Thanks all for coming and waiting to see this talk. I would like to talk about 6 Akka anti-patterns that were actually solved in Akka 2.6. Akka 2.6 was released not too long ago, so I didn't have time yet to find the new anti-patterns. So I'm going to talk about the ones that are not there anymore. Why am I talking about this? Well, I had this talk in 2017 called 8 Akka anti-patterns you would better be aware of. And back then, the reason to give that talk was that Akka is a tool that you have to understand well, otherwise you can't shoot yourself in the foot. And the 8 anti-patterns were ways to sort of do that. And now this talk is basically, I collected all of these anti-patterns so far. I've got them on my website if you're interested. And these range from beginner mistakes to like mistakes that even experts do from time to time, or that just creep in and grow as your project gains in age. And the nice thing is that many of these have been addressed in 2.6. So this is what I want to talk about today, mostly those things that have been addressed. Just a quick thing about myself. My name is Manuel Bernhardt. I work as an independent scuba diver and sometimes consultant. What I do for a living is to help companies get started with reactive systems, or to help them when they've got one in production and they have a critical issue and everything comes crashing down. They also tend to call me. I'm also a Lightbend consulting and training partner. I wrote a book a few years back called Reactive Web Applications on the topic of building reactive web applications with the Play framework and Akka and reactive streams. And let's go and talk about Akka 2.6. So this is a major release. The Akka team does not do these point releases. They don't take them lightly. This is a lot of work that goes into that. So the past major release 2.50 happened in April 2017. That's been almost 2.5 years, if I'm not mistaken. And it introduces as a highlight the Akka typed API. So this API was there before, but it wasn't really stable. It kept on changing, but now it is stable, production ready. And the important thing to say here, this does not replace the classic API by any means, okay? It's not like you have to migrate over or anything like that. You can continue using it, the classic one. It will continue to be maintained, but they can exist side by side. That's the nice thing. But the typed one, as we'll see, introduces quite a few advantages. Artery is a new default transport protocol, transport layer, which offers quite a few advantages. And then there's many improvements and fixes, and we'll go over a few of those. So let's get started with the first anti-pattern, shall we? If you fail to plan, you're planning to fail. So you may know this quote, and you will notice that, by the way, that during the talk the quotes are a bit dark, but yeah, that's just how the talk is. Quote by Benjamin Franklin here. And the first anti-pattern is about not defining a protocol. So what does that mean? Well, you can get started writing and building an actor system and just create your actors and then invent messages and pass them around, and this will work. You will get to a working system quite quickly. But then on the medium and long term, this can become quite problematic. So what can go wrong, for example? Well, for one, the responsibilities in your actor systems, they might not evolve in a coherent way. So you might end up with having split responsibilities in different parts of the system. And this will just keep on happening over time without you planning for it necessarily. Then the other thing is that you will end up having things being tightly coupled because you know, for example, you're thinking, oh, it's quite innocent. I'm going to reuse this message here, and I'm going to pass it along, or this event, pass it along. And then before you know it, your actors depend, or the protocols themselves actually depend upon each other. They also need to know about each other's protocols. They need to understand details from other actors that they shouldn't be concerned with. And then if you want to sort of separate, for example, one part of the system, that's going to be tedious because you have all of this glue happening. And then finally, and this I've seen quite a bit actually, a message is flying around in the system. I mean, it's fast and all, but still, it takes some resources. And there is no need to pass the messages in some cases. These are things that happen and evolve, and you don't notice it or you notice it. The difficult thing with the classic API is that there is no help from the compiler to refactor your actor system. It's really hard. If you want to touch things, you have to rewrite all the tests, you have to be really careful, and you don't have any help. You're on your own. The only way you send messages from one point to another is by addressing them by one reference, which could be anything. So how do you go about not defining a protocol in Akka 2.6 or Akka typed? Well, you can't, which is a great thing about that version now. Because Akka typed, the API forces you to define a protocol. To the very least, you have to define a top-level message here. And what you need to specify is the protocol or the type of message that an actor can understand, and when you're building messages, the type of reply that they expect. So let's look at an example here. This would be the marker trait here, seal trait configuration command. This is a marker trait which tells me what my root protocol is. And then the actor that supports this protocol, I would define when I'm using the object-oriented style of the API by extending the abstract behavior of configuration command. And I also have to pass in here a context that is also typed. So the thing you notice right away is we have types here. And for an example of a message here with this API would be that I define a message class, for example, retrieve configuration. And that is extending this marker trait that I have here. That's the one thing. The other thing is, if I'm specifying, I have to specify, that's a big difference if you're used to the Akka Classic. I have to tell it if the message needs a reply, and this obviously does. Retrieving a configuration, you would expect a response. If you want a response to that, you have to define, tell it where to respond to. And the response here is a typed actor reference, which is to say that it tells you here the type of the response. You can't just reply with anything at random. You have to tell it, this is what I want as a reply. So for example, in case of success, I could say that the configuration was found. That's a successful configuration response, but I could imagine that I have one where the configuration was not found or things like that. So I'm basically specifying what I'm really expecting. Now, that's nice because I can't do the beginning mistake of sending a message to the wrong actor. That happens when you start. But that doesn't tend to be a big problem in my opinion, and in my experience either. Over the long run, you sort of tend to catch these things and fix them. What's nice is that the message paths are now checked by the compiler, and the compiler can help you refactor them. It can help you change them. But the nicest thing, and this is another example I'll show you, is that you can infer the intent of the protocol. You can read the story of the protocol, what it wants you to do with your actor system, just by looking at the trail of these actor references and the messages. So let's look at another example. I have two actors here. A banking actor, that's sort of the entry point, the API to your banking system, and then a session actor that it creates. So let's say you log in, you create a session. So the first thing you got to do is to send a login message here. So this banking actor up there, it expects a message of type banking command. So a login, for example, which is a banking command. And this login tells in the protocol reply with two actor references of type login response. So if you read this, you know what you need to reply here from this, or what you will get back when you send this is something like that, the login response. And then the login response could be, in a successful case, that you're authenticated, or in case of failure that you're not. So you sort of right away see that there is a link between these two things here. You know in which order this goes. You can't mess up the order of sending or receiving or expecting what's going in or out there. You see that right away just by looking at the signature of the message. And then finally, here, once you've done that little game, you got to create a transaction, and you could go on and expect a response to that command, etc., etc. So in my opinion, that's really the nicest thing. If you look now at the protocol, if you define it, if you look at it, you see the story behind the protocol. And I think that's the most powerful feature in 2.6, honestly. Okay, so that's one of the things I wanted to talk about. Another nice quote, Time is a storm in which we are all lost. We get more and more philosophical as we go on. William Carlos Williams said that, and this anti-pattern is about race conditions. So what do I mean about what do I mean with race conditions in the context of Akka or actors? Well, with the actor model, what you would expect is that inside of a message, you're in this nice, quiet world where you don't have any concurrency, where your messages come in one after the other. You know what to expect. They happen one after the other. You don't have to worry about mutexes, about synchronized things. You can use mutable state and it's safe, it's nice, except if you do this. And by this, I'm taking an example in the classic API where I have an actor, I have some state here, the transactions, and then when I'm receiving this message process transaction, I'm going to ask another actor here, this means ask, I'm going to ask this other actor, please process the request. This returns a future, and the future is an asynchronous computation. And here is the problem. When I'm then handling the future in this way, by waiting for it or expecting it to happen, to finish, I'm closing over mutable state, I'm going to run into trouble here. Because it might just be that while I'm doing this, something else is running at the same time, and then I might lose my state. You see, because the actor won't stop processing messages. It will continue to process messages. And that might be problematic, I would think. Now, in general, it's problematic to use asynchronous constructs in an actor. It's error-prone. I've seen even the most experienced developers do it from time to time. And when you look at the classic API, the way to go about it is to use the pipe pattern. Except that sometimes you just forget to use the pipe pattern, or you didn't read the documentation, or you don't know about the pipe pattern. So the way it's solved now, or the way it works in 2.6, is that you can't do that. You cannot shoot yourself in the foot in this particular way, because now if you're using the ask pattern to contact another actor, you have to return a message here. So this ask pattern is still something asynchronous, and then either this asynchronous computation succeeds or fails, but the result that is expected is a message. And that changes the game, because now this message that is returned, it will be sent to the actor, and then you're back in the synchronous illusion of things happening sequentially, where one message happens after another, and you don't have this problem anymore of two threads talking to your state, to the same mutable state. Third anti-pattern. Some men aren't looking for anything logical, like money. They can't be bought, bullied, reasoned, or negotiated with. Some men just want to watch the world burn. That's Alfred in the Batman The Dark Knight, very nice movie. And that anti-pattern is about blocking. So how can this happen? This can happen if you're calling a synchronous API. Okay, you know it shouldn't do that, so you're calling an asynchronous API instead, except that sometimes you're calling an asynchronous API and you don't know it, but that calls another library, and that library ends up doing something blocking. And then you're in the same situation anyway. Or you're explicitly waiting for an asynchronous computation. You shouldn't do that really, not in production code. Do it in the tests, but not in production code. So why is that a problem? Well, let's look at how Akka ticks. So Akka is working like this. It has a thread pool that's backing it, like an execution context. There are little threads in here, nicely drawn. Then I have actors with their messages in the queue, and I have this component called the dispatcher, which takes care of giving threads to actors. So the way that works is that one thread is handed over by the dispatcher to an actor, and then it has the thread for a number of messages. By default, the batch size is 5, yeah, in this example, it's just 2. So the actor can process 2 messages or a few messages, then it has to give the thread back. And then the same thread can be passed on to another actor for it to do its thing, and so on. And that works so long as you don't block. Because the moment you start blocking, your threads will be stuck with these actors doing whatever, waiting for a synchronous API to reply. And if you do this long enough, you're running out of threads, and then you're in trouble. This is called thread starvation, and this is really difficult to observe, to debug. Even to profile. It's hard to get to that point on the system where this happens, because usually it happens for a bit, and then it goes away, then it comes back. This is really tough to figure out. So how can you bring down Akka 2.6 by blocking? You can't. Well, at least you can't bring it back down the whole of Akka. So what happens in 2.6? There is a new internal dispatcher, which runs the internal actors that Akka defines. For example, in the cluster module, there is this one actor that is responsible for replying to heartbeats from other nodes in the cluster, the failure detection. That can't be hijacked anymore. Well, it can be hijacked by other things like garbage collection, but it can't be hijacked by your thread pool being exhausted because something is blocking all the other threads. So you can still starve all of your actors to death, but you can't starve the internals of Akka to death. So the whole thing, the thing as a whole, gets a bit more stable. This is the way the world ends, not with a bang, but with a whimper. T.S. Eliot. Akka anti-pattern number 4, using Java serialization. And this was very easy to do, to achieve prior to 2.6. You just had to leave the default on. By default, if you weren't doing anything, Akka was serializing your messages with Java serialization, which kind of works if you're just staying in memory on one node. But if you're using Akka, probably you want to go on multiple nodes and do stuff in persistence on disk as well, or in a database. And then you get these nagging warning messages, but you could ignore them. And then eventually you run into trouble. Because what happens? The messages that are serialized, first off, it's going to be slower than a proper serialization format. And then second, it's a very poor candidate, Java serialization, for protocol evolution, changes in the class, removing a field, adding, renaming, what's on, what's not. And this happens both when you persist things to disk and when you're sending things across the wire in the cluster. And then finally, and I think this is one of the bigger issues actually, is it has very poor security. There's a lot of holes in there, and you can really cripple a system that relies on Java serialization. I once had a client that lost an undisclosed amount of money, but it was a lot of money, like multiple times of what I asked them to help them fix it, because they were using it, they had a running system, they had to roll back to a previous that made some changes in the protocol, they had to roll back because there was a bug, but while they were running the new version, they had changes in the journal being written, and when they tried to run the previous version, that didn't work either because it wouldn't recognize the new thing. So it was crashing, and I had to fly there in a rush. That was a stressful thing, a bit like coming here and trying to catch the right train for this talk. So how can you use Java serialization in Akka 2.6? You can't. Well, at least not by default. And there is a new default, which is using the Jackson serialization. And I have to say that that's pretty neat. Even though I had some restrictions about Jackson, you know, this library, and you have to use all these annotations. But it turns out that there is a very decent binary serialization format called CBOR. And actually it works in most cases. So in order to use this, you need to define a marker interface. Then when you define your messages, just use that marker interface, and then in the configuration, just tell the Akka that these messages of this type should be using Jackson CBOR. And that's it. Then you've got a pretty decent serialization out of the box for free. And I'm putting this out there because the default go-to solution in prior to 2.6 that I've seen everyone doing is protocol buffers. And protocol buffers are nice, but if your system only stays inside of Akka, or at least inside of the JVM, they're quite expensive to maintain and to write and so on and so forth. And I'm saying that because if you're communicating with services on the outside that are written in Go and Rust and whatever, you might want to use something that has multiple language support, and Jackson would not be a good solution for that, I don't think. But at least if you're staying inside of the JVM, this is a very decent solution. So and it should work also performance-wise for the most projects. So definitely worth checking out this one. The desire of excessive power caused the angels to fall. Francis Bacon. Using Akka remoting. This directly. So what's this about? Anyone seen this movie? Apocalypse Now, which I thought would fit the theme of the quote. So Akka remote is a mechanism by which you can establish a peer-to-peer connection between two nodes. Okay, this is the basis for clustering in Akka. Now the problem is, if you're using it, there is one thing you should know about is the quarantine nodes. So this means that if there was a hiccup with the connection and you're trying to connect back, then you can't do that unless you restart the remote actor system. And that's quite a problem. And I've seen that, I haven't seen it in recent times, but I've seen this quite a bit earlier on. People were writing their systems directly on top of Akka remoting. And that's a problem because Akka remote is this thing that allows you to sort of establish a connection between two nodes. But then the moment you do that, and the moment you're entering the realm of distributed systems, there's a lot more to think about than just this one connection, this one link. It's not trivial. So 2 years ago, I went into this frenzy of reading a lot of papers. I still do that from time to time, but this is what my floor looked like in the office. And this is all just foundations for doing this thing called a membership service in a cluster. And that's not even scratching the surface. This is just like some of the basics. You haven't seen the rest of the office. And the point here is that this membership service building is a lot of work. It's hard to get right. And Akka didn't invent it from scratch. Jonas didn't just invent that from scratch. He was inspired by quite a few other database systems or distributed systems out there. And the membership service is this real, complicated beast to get right, and there is some trade-offs to be made that you have to be aware of. So in order to not shoot yourself in the foot with this, in 2.6 you can't use remoting directly anymore. It will only work, it will only be enabled. You can only do remote deployments on remote nodes if you're using the cluster extension, but you can't access that module anymore directly in 2.6. And then if you want to learn more about Akka Cluster, there is Akka Cluster is this thing that gives you a lot of primitives for building distributed systems, gives you the membership service, and I've wrote a few articles on that topic here and up here a little bit as well. So if you're interested in checking out the capabilities of that. Now, next anti-pattern. There are two ways to be fooled. One is to believe what isn't true. The other is to refuse to believe what is true. Also very philosophical quote by Søren Kierkegaard here. And the sixth anti-pattern is using auto-downing. So what's a bit of theory here from the papers. Group membership with a single group is impossible when there are nodes that are suspected of having failed. And you only need one node in suspicion of having failed. What does it mean? Akka provides you this illusion that all the nodes in a cluster are part of this one system. And it tells you exactly, it maintains the view of who is there and who isn't there. Now, if one node is suspected of being in trouble, of not being there, you can't maintain that illusion anymore. You can't try to trick it and say, oh, it's only one, I'm going to remove it, and then it's going to be fine. No, the theory shows that it's breaking. It's based on the FLP impossibility principle And you can't have consensus basically as soon as one thing is suspected of having failed. So a leader in a cluster or in Akka, the leader cannot make membership-related decisions when you have one of these members being flaky. So you have to remove it on your own, or sort of you have to tell Akka, let's just by hand, let's remove this thing. And when would something like this happen? Well, you could have one node crashing, bad luck. Or you could have a network partition. But what I hear often, and more often than I would like you to hear, especially in larger companies, network partitions don't happen. You know, we never had a network partition in our network. Our network is reliable. We're using EC2, we've run it so many months, we never saw a network partition, it can't happen. And that's fine and all, unless you're using, you want to use Akka cluster for managing persistent state. Now, if you want to use Akka cluster, but you don't have any persistent state, don't use Akka or a cluster, or don't use Akka for that matter. It's the use case for Akka is to have persistent state that you have somewhere in databases, but you want to lift it into memory and have it there to be really fast, but have it replicated everywhere. If you don't have state, then there is not much of a point. You can just have a stateless service and write it in Go, or whatever else language. You don't need the whole cluster thing around it. And it turns out that network partitions do happen. There's quite a bit of them. There's quite a bit of them in EC2 as well. And there's global routing failures. It can happen at any level, small, big, it doesn't matter. It will happen if you're leaving your network running long enough. And actually it happens quite a bit in EC2. Micro partitions, really quick ones, silent ones. Sometimes it's fast enough so you don't detect anything. Sometimes it trips your whole thing over. These were screenshots taken from this excellent article. It's from Afir. It's called "The Network is Reliable." Quite a nice collection of things here. And really, the thing about network partitions is that it's not a matter of if it's going to happen; it's a matter of when it's going to happen on your system. Okay. So this brings us back to Akka, because in Akka, if you have a network partition and some nodes are suspected of having failed, the leader would say, hey, I can't do anything anymore. So you can't add new nodes, you can't remove nodes, someone has to make a decision. And the way this is done is by defining a downing provider. And then there used to be this thing called auto-downing, and pretty early on in the documentation, this had this thing, do not use, written there. And for some reason, I don't know why, people tend to ignore that flag, or tended to ignore that flag, and there is even, I didn't screenshot it, but there's a big red box below this part of the document saying, don't use this in production, it's not gonna work, etc., etc. And what does this do? This is a very naive algorithm. What it does is, here you have your Akka cluster, it's a pentagram as it should be, and here you have a network partition. And then if you use auto-downing, what's going to happen is each side will assume that it is the surviving side, the side that's not at fault. And so you will have two islands here. And if by chance you have state on this side and state on that side, and they can still talk to the outside or continue writing things to disk, then you will enter a scenario where, depending on the sensitivity of your state, you will have a situation room with a lot of business people in there on Excel trying to stitch together data. So I've seen that. It's yeah. Don't go into that. So you're guaranteed to get a split brain scenario if you're using auto-downing. How can you use auto-downing in Akka 2.6? You can't. It's gone. It's removed. So you can't do that anymore. Tough luck. So what you have to do is to use a proper split brain resolver, or should I say a split brain preventer, I would call that, because the split brain resolver, it's too late. If you have a split brain, you're good luck. So it's a split brain preventer, something that will not let it happen, this scenario. Which one to use? Well, Lightband has one that is written by the people that do Akka, so I would recommend using that one. There is some open source alternatives. Now, that being said, I did a review 1 year or longer ago for a client where I reviewed all of the implementations, and back then I couldn't find any one that was correct. So that's at your own peril. Or you can roll your own, which I've seen sadly more often than I would have liked to. But seriously, don't do that, because if you look at the implementations, they're mostly wrong. It's very naive. It's a sort of, oh, we're using this. No, don't do that. No. All right. And then for the last anti-pattern, being out of touch with the hardware. Anyone knows this? Yeah? So this is Kubernetes. So today I think Kubernetes has won the race or the war or whatever you want to call it. Everyone, even the companies that really shouldn't, use Kubernetes. This is the default layer that you have on the bottom of your infrastructure these days. And then there's a very nice quote by Martin Thompson, who is like a really performance guru out there. Hardware tries so hard to make software fast. Software tries so hard to make hardware slow, and I think software is winning. So how does Kubernetes work? You have nodes, and nodes have pods in them, and the pod is where the Docker container is running. Okay, and then you have more nodes, and basically Kubernetes is scheduling the pods on the nodes. Okay, easy so far. Now then, what you can tell Kubernetes is that a pod should get a certain amount of CPU cores, and this is why here you have a little blue arrow, is because I'm trying to point to a core. So most CPUs these days are multi-core, but you only get one of the cores, okay? Is anyone here using AWS by chance? Because if you do, then the CPUs there are actually a hyperthread of a core, which is to say they're not a real core, they're a virtual core. And if by chance both hyperthreads are busy, then one is going to win. Okay, so in reality you don't have 4, you have just 2 cores for your pods, if you have configured it this way, to have 2 vCPUs per core, per pod, sorry. If you remember what we were running earlier on with the dispatcher and the threads, that's what you run in Kubernetes now, in the pod, and the thread, when it wants to run, it needs to have access to a core, okay? Now, to make things worse, more often than not, especially if you're using EC2 and EKS and so on, your nodes, your Kubernetes nodes, they're not real hardware machines. They're an instance in a real hardware machine, okay? So here, you've got your real hardware, you've got the hypervisor of EC2 that is assigning the cores of the real CPU to the instances, and then the instances go on and share that across the things in Kubernetes in the pods. And you have a lot of contention, and basically what happens if you're not configuring this right, your system is going to not work at all. And I just had this like literally 2 days ago with a client. And then also, I mean, I have this all the time now. This is great for me and business and all, but but this is not like, in reality, it's not really good. So what's happening? For example, let's take a Kubernetes deployment where you say, I'm giving 2 vCPUs to each pod. And this is, you would think, no, why are you doing it? This is very common. People, because most operations people, they're used to single-threaded services. And so they're just assigning these 2 CPUs, 2 or 4 or whatever. Then you have the EC2 price to pay where it's hyperthreads and not real cores. And then if you look at the default configuration, you've got 16 threads for the default execution context if you have 2 cores configured. 16 threads for the internal dispatcher. So you have 32 threads that are contending for 1 real core down here that itself might or might not be scheduled fairly across the instances in an EC2 hardware instance. And what happens is that your nodes keep on flying out of the cluster, and your clusters keep on not forming correctly, and things go really haywire because you don't have enough real cores, CPU cores, for your Akka application. So How do you solve that in Akka 2.6? Well, you can absolutely shoot yourself in the foot in this way in Akka 2.6 as well. Okay? This is not one of the anti-patterns that's solved. Akka can do a lot, but let's face it, it can't do magic. It can't teach you, it can't reach through the virtualization layer and sense what's really below what the hypervisor tells it, okay? So this is something where you have to be careful, learn the basics, know your infrastructure, and then configure by all means your Akka application correctly to run correctly with that in that regard. All right, and I think, yeah, we're just a bit above time, so I think that's about it for now. And yeah, thanks for waiting and listening. Thank you.